Hello students, welcome again to our podcast. I'm really excited that this podcast is really coming a long way, and I'm getting into a rhythm of making these videos. It's really fun, it's exciting. I'm thinking about having a new format. Right now I'm just using kind of scratch paper, but I'll get like a book or something. But anyways, here we go. This is our next lesson in terms of solutions. So far we've been talking about concentrations of solutions and a very brief overview of the different types of solutions. We've been talking about molarity, moles over liters, talking about molality, which is moles over grams. Okay. We've been also talking about the mole fraction, moles over moles. We've been talking about parts per million, essentially grams over grams, the times a million, right? This is for solutions where we have very, very dilute solutes. And we've been also talking about percent composition. Okay? And these are all great and everything, but I wanted to talk about some of the physical properties that are affected through solutions, because that's where a lot of the chemistry really comes from. And these properties, we would call them colligative properties. Yes, colligative properties. Essentially, there are three properties of liquids that are going to be affected when we create a solution, essentially dissolve a solute into a solvent. The first is vapor pressure. The second is boiling point, which is affected. And third is the freezing point. I'm going to abbreviate these: boiling point, freezing point, and then that's just vapor pressure. Let's start off with vapor pressure because this will help us explain boiling point. Let's say we had a pure beaker of water and had a bunch of water molecules. All right, I'm trying to draw the bent shape here. My drawing again is not the best, but working on it. And these water molecules are essentially pushing, or they're flying around. Even though they are a liquid, they're still moving around a lot, and they're hitting the walls of the beaker and the bottom of the beaker. They are also bumping onto the top or the bottom of the surface of the water. Okay, and they're creating a tension. They're creating a tension, and so pressure essentially. We also know that there is atmospheric pressure pushing down onto the surface of the liquid. And this is essentially also keeping the molecules down, the water molecules down. Now, let's say we add a fire, because we just love fire, or we shock this with lightning, and we raise the kinetic energy of the molecules. There comes a point where the molecules, their pressure pushing up exceeds the atmospheric pressure. And at this point, we get vapor pressure. We get the pressure of the liquids leaving the liquid state and becoming a gas. Okay? And this can come in the form of evaporation or, again, boiling. Okay, we see that. Now, what do you think might happen when we add a solute? Let's say like NaCl. We stick it in. Okay, well, a lot of us would answer, yeah, well, we get Na plus ions and Cl minus ions in solution. Okay, but what does this really look like? What does this really look like? Well, if I were to expand this a little bit, here's my big beaker. Here's the water level. And we had water molecules and NaCl ions. Here's your Na, here's your Cl, and here's another Na, and here's another Cl, and here are your water molecules. Okay. Again, vapor pressure has a lot to do with the surface area of the liquid that is exposed. And a lot of us know that if we were to boil water with a larger surface, it would essentially boil faster. There would be we would lose more liquid. There would be more gas coming out, more steam coming out. You can also see this with big puddles. Puddles tend to shrink faster than small puddles do. Okay, or puddles that have larger surface area. In this case, the same kind of application applies. We have water molecules that are pushing up, okay? But because we have now ions, like the Na ion and Cl ion in the way, they act kind of like roadblocks. They don't allow the water molecules to hit the surface of the water, okay? And so the vapor pressure decreases when we add a solute into a solution, into water, or we create a solution, okay? And this is what we call a colligative property. It's a property of solutes in a solution. We are changing the vapor pressure. And colligative, what it really means is that it doesn't matter what the solute is. It could be sugar, it could be polar, it could be non-polar. Whatever it is, it changes the vapor pressure all the time. Okay? Now let's move on. Here we go. Boiling points. An interesting property when we add a solute to, let's say, water, the solution, is that the boiling point increases, meaning that if we had a beaker again and we had a fire, and we all know that water boils at 100 degrees C, okay, but in this case we added NaCl into the solution. The normal boiling point would be 100 degrees C, but if we were to add, say, 30 grams of NaCl, essentially the boiling point, I'll say this will be boiling point not, this will just be boiling point, will be around 106 degrees Celsius. Okay, interesting. And we'll talk a little bit more about why this is in class, because I'd rather have a shorter video here. But there is an equation which allows us to predict at what temperature the new boiling point would be. Essentially, all we have to do is to find the change in temperature, the delta T, the change in temperature, I'm going to TB for T boiling, is the molal boiling point elevation constant times the molality. Interesting. Okay, this is the molality of solution, or solute, okay, of the solute. And here, this is the molal boiling point elevation constant. There is one for every single type of solvent or solution. Or actually solvents, okay? For water, the KB for H2O is 0.51. And there are units. It's Celsius per mole. Okay? The KB for, I don't know, acetic acid, C2H4O2, is essentially 3.22 Celsius per mole. Okay, so these are all constants. It depends on the solvent that you're dissolving in. Okay, and as you probably would have guessed, the next point is the freezing point depression. Okay, essentially, also when we add a solute to a solvent such as water, we will also lower the freezing points. I should have said melting point to be more accurate, but I'm just going to say freezing point because some students they connect better with the idea of freezing. Okay, the freezing point, the melting point decreases. Okay, so again, if we had a solution here, let's say this is like H2O, 2O, and we had NaCl, and we're putting around 30 grams of this into H2O, and we stir it around, mix it until it dissolves, and then we put this in an ice box. I'm going to try to draw some ice cubes. Don't judge my drawing. Yes, okay, we have some ice cubes. Okay, essentially, normally we know that the freezing point is 0 degrees Celsius, but in this case, the freezing point might be, so this is a freezing point not. The freezing point might be around -6 or something degrees Celsius, or the other way. Okay. And the same type of equation applies to find the change in temperature that allows us to see the new freezing temperature. Okay, is TF for freezing equals KF. This is the freezing point depression constant times the molality. Okay. Again, this is the molality of the in terms of the solute. Okay. And again, just like the boiling point, the freezing point, there is a constant for all solvents. For H2O, the freezing point is, or the KF is 1.86 Celsius per molal. Okay. Okay, so this is pretty simple, and there's interesting applications to this. Okay, so if you have ever cooked noodles before and you've seen your parents put salt in the water before you cook the noodles, this is essentially why. Okay, you can get the water hotter than it normally is. Same thing with freezing point. Have you ever seen on a really cold day there is snow or ice on the road and then they're salting the roads? Okay, we're lowering the freezing point so that there's no ice on the roads. Okay, but we'll talk a little bit more about why this happens. Okay, this is a little bit more connected with vapor pressure, while this is not so much so. Okay.